So now that we've explained what a forcing is and the kinds of responses that can produce, what are the actual forcings on the Earth's climate? What are the natural forcings and what are the forcings as a result of human activity? So this figure illustrates 6 different forcings on the Earth's climate, left to right, and the magnitude of those is in watts per square meter. So if you remember, the amount of energy that's making it into the Earth's system from the sun is 239 watts per square meter at the surface, 340 watts per square meter total amount of sunlight input to the planet over the averaged over the surface of the Earth. That's that 1360 divided by 4. It's 340 watts per square meter. Some of that immediately, a huge fraction of it, 30%, is just reflected back into space. The remaining part is absorbed. But let's think about the 340 because some forcings can change how much of that is reflected or not. So that's our sort of scale of the energy flow at the surface of the Earth, 340 watts per square meter. And you notice these forcings are all quite smaller than that. This is 1, 2, 3 watts per square meter, so less than 1% of the total. So these are perturbations. If it's a positive forcing, that means it's putting more energy into the system and therefore would lead to global warming. If it's a negative forcing, that would lead to global cooling. So greenhouse gases that are well mixed in the atmosphere, primarily carbon dioxide, are the dominant forcing of the ones that we see here. On the far right, you'll notice solar. That's fluctuations in the natural fluctuations in the sun's output. And that's a tiny little change, maybe a tenth or less of a watt per square meter. Uh, Land use albedo. As we deforest the planet, we are making the planet brighter and therefore more reflective and therefore cooler. So if you wipe out the Amazon rainforest, you replace dark, absorbing, leafy vegetation with bright, reflective desert sand, and that's a cooling effect. Of course, you've also eliminated and introduced a huge amount of carbon that was stored in those trees into the atmosphere, and you have eliminated one of the ways that CO2 gets absorbed, which we'll see later when we talk about the carbon cycle. But just the change in reflectivity is a cooling effect. Aerosols are small particles that are suspended in the atmosphere, and they can both reflect sunlight back to space, which would cool it, and they can be more efficient radiators of the Earth's radiation, the warmth of the Earth's atmosphere into space. So uh, they're not huge effects. It's hard to calculate them exactly. It's possible that the direct effect of the warming of aerosols can have a warming effect on the planet, but they're maybe in the negative side. And ozone is another pollutant that can absorb some solar radiation and lead to a little bit of an increase in the overall energy balance. So that's the magnitude of the forcing, and the takeaway from this slide really is that the anthropogenic forcing is the increase in carbon monoxide and methane in this first column, these guys primarily. It is a much larger forcing than any of the others, in particular the solar forcing, as we see. Where does that CO2 come from? It mostly comes from burning fossil fuels, but there's a non-trivial amount that comes from producing cement, believe it or not, as well as land use changes, as we just alluded. If we wiped out the Amazon rainforest, we'd be burning a lot of wood. That would put a bunch of carbon into the atmosphere. Total human carbon emissions at the present time are a little bit more than 10 gigatons per year. And the note indicates that over geologic history, in our record going back tens of millions of years, the fastest rate of carbon injection into the atmosphere was about 10 times smaller than that. And it actually led to a significant enough climate change to create a mass extinction event. Let's take a look at those different greenhouse gases. Uh, Carbon dioxide, methane are the two that we talk about the most. Water is also a greenhouse gas, and there's sort of nothing we can do about that. The Earth is a watery world. It is covered with oceans, and there is a water cycle going on. If the Earth gets dramatically colder, then you would freeze those oceans and not have clouds. If it gets dramatically warmer, it would probably be completely covered by clouds, but that's not something we can control. Carbon dioxide in the top row, this GWP stands for global warming potential. And so the units are meaningless. It just says if we say the global warming potential of carbon dioxide is 1, what's the global warming potential of these other things compared to carbon dioxide? And they're all much greater global warming potential than carbon dioxide. However, most of them have a much shorter lifetime in the atmosphere. That means you produce a bunch, but it very quickly gets destroyed. The bottom line, as an exception, CF4 has a longer atmospheric lifetime and a much greater global warming potential. Happily, there is very, very, very little of it in the atmosphere. So we're mainly going to be taking a look at those first two rows, carbon dioxide, which the amount of it, if you put a whole bunch new in the atmosphere, the amount will change over time, but it will last for hundreds of years. Whereas methane, if you put a bunch in and then go away and don't do anything else, it'll be gone in 10 or 20 years. So this shows the history of the abundance of methane and one of the chlorofluorocarbon molecules, which has been used in air conditioning and refrigeration over the course of the past couple of hundred years. And you can see a dramatic increase in the abundance of those molecules over time. And then more famously, the increase in the amount of carbon dioxide in the atmosphere over time, going back to the beginning of the Industrial Revolution, where it was at about 270 parts per million. And that works out to about 0.027%. And it is now over 400. This chart is a little bit out of date, and it's increasing quite rapidly. In the inset, you can see that there are seasonal fluctuations, and that's really cool because those seasonal fluctuations are a result of, in the summer, in the northern hemisphere summer where these measurements were taken, when plants are growing, those plants grow by taking carbon out of the atmosphere and using it to build new plant cells. So in the summer, there's a dip in the amount of carbon dioxide in the atmosphere, and then when they die and those leaves rot, or the cycle of growth of the plants goes through the winter cycle, that carbon is released back into the atmosphere. So you see an annual cycle in that inset, and it would be offset by 6 months if we looked at measurements taken in the southern hemisphere. Now let's zoom out and take a look at a much longer period of time. And you can see if we go back 1,000 years, quite constant at about 280 parts per million up until the Industrial Revolution, when we really started burning fossil fuels at significant rates. And we're now at about 415 parts per million. And throughout this module, you'll see in the slides and in the pages links to various government websites and nonprofit organization websites that provide up-to-date information about the amount of the various greenhouse gases, including carbon dioxide, over time and up to the present time as well. And we're now at about 415, 416 parts per million. And again, in the summer in the north, it's a little bit low because a lot of it goes into the plants. It'll go up a year from now, it'll be even higher. Then if we zoom out even farther, 450,000 years, you can see that there have been periods of dramatic and fairly rapid changes in the amount of carbon dioxide in the atmosphere. But all of those changes were going to smaller values and not larger values. That over the course of the past 400,000 years, the highest it has ever been was that pre-industrial value of about 280 parts per million. And those periods where the CO2 is high corresponds to what are called interglacial periods, and where the CO2 was lower, down around 200 parts per million, those were ice ages. So the dominant global climatary condition over the course of the past 500,000 years was ice age. And when the CO2 went up to around 280 parts per million, climate changed very dramatically. The ice melted, and we have the nice, pleasant climate that we've been enjoying for the last several thousand years. Now we're going in the other direction, saying, okay, I don't drop it by 150 parts per million, I'm increasing it by 150 parts per million. What's going to happen then? And we have some information about that by looking back into the geologic record. And how do we get that information? We drill into deep cores of ice on land ice on Greenland and Antarctica, where every year there's snowfall that traps bubbles of the atmosphere from that year. We drill these very deep cores, and we can see the layers year after year after year, as you see in this picture here, the annual layers, so we know we can count the years back, and we can take air samples out of those little bubbles of trapped air deep, deep in the core. And then we've got an air sample of the atmosphere from going back hundreds of thousands of years. And when we do that, we're able to measure the abundance of different isotopes of the molecules in the air. And the book explains this in some detail, but you'll remember isotopes are the same elements, but different weights, different numbers of neutrons. And as it happens, chemical reactions are affected by those different isotopes, and the rate that they occur depends on the temperature of the air, depends on the temperature of those molecules having that reaction. So the abundances of those isotopes is a thermometer, is a way to measure what was the temperature of that air when it got sealed in that air bubble. So we can actually measure the temperature of the air going back in time. And what you see here, we're still just looking at methane and CO2 concentrations from these air bubbles going back in time. You can see that methane and carbon dioxide are doing about the same thing, going back and forth, fluctuating in tandem with each other. When one goes up, the other goes up, and vice versa. And we know, and as we will see in later parts and in the next module, that when the CO2 and the methane are high, the temperature is high, and when the CO2 and methane are low, the temperature is low. So take a look at some of the links that are available to you where you can see animations of the CO2 abundance over time. Again, this is a slide made a couple of years ago, so it was showing 407 parts per million of CO2 in 2017. You can go to this website and get an up-to-date number, and if I click on it right now, CO2 now.org, I find that on the day that I'm recording this, it is 416.39 parts per million. So it's gone up from 0.027% to 0.041% in the last couple of hundred years. And in the last 50 years, it's gone up very rapidly. So take a look at a lot of these resources are showing you what the evolution of these greenhouse gases is in our atmosphere.